Jai Shri Gurudev. Dear students, today I'll be starting with Module 3. This is the first session of Module 3. Title of Module 3 is Time Response of Feedback Control System. So in this particular module, we are going to analyze the first order and second order system using feedback, and you will be determining the time response of a feedback control system for these two orders of the control system. Coming to the outline of this particular module, first we will discuss about the standard test signals which is used to determine the time response of the system, and among these standard signals, unit step signal is taken as the standard signal which is used to find out the step response of the first order system and second order system. So we'll try to find the unit step response of the system, that is first and second order system, using the corresponding time response analysis. Then you will learn about time response specifications of second order system and first order system, and we will discuss about steady state errors and error constants. Then a brief introduction about PI, PD and PID controllers will be discussed. Finally, we are going to take a few important problems on all these topics. So this is the outline of your module 3, which we will be taking one by one. Now in the first session, we will discuss about standard test signals. I'll just give you a brief introduction about important test signals which is used for the analysis of the system. Now coming to the introduction part, in time domain analysis, it is very important to find the response of a dynamic system to any kind of input which is expressed as a function of time. So we will be taking one input which is defined in terms of time, and using that input in the time domain we will be finding the output response of the system. That is what you mean by time response. Now it is possible to compute the time response of a system if we know the nature of the input and the mathematical model of the system which we are using. And these two things you must always know if you want to find out the output response for a system. And generally when we take up any input signals for a control system, first you have to decide what is the type of the input that you need to give for that system. Okay, so you are supposed to know fully ahead of a time, so what is the input that you are giving for the system. So generally initially we will not be knowing, but for example if you want to just find out something, so you should know what is the type of the input that is needed for that particular system. For example, if I consider a radar system, a tracking system, the position and the speed of the target to be tracked may vary in random fashion, but initially I will not be knowing it, but I know there is a target which might come across in the tracking field, but I will be knowing what is the type of the target it might come, or what is the speed of that target, that is unknown to us, correct? So it is therefore it's very difficult to express the actual input signals mathematically for any single equation. So generally I cannot judge this could be the input. I can just analyze the system by taking some input, but definitely you cannot say this will always be the input for the system. So that depends on your application of the system. This is what it means. Now coming to standard signals, that is what, so since we cannot judge the type of the input we might get for a system, so we are taking some standard test signals, and using those test signals we are analyzing the given control system. So if the system works for this standard signals, it can work for any other type of the signal which you might come across. That is why testing of any system with the standard test signal is very much important, and you need to use these standard signals for analysis of the system in the time domain. So the characteristic of your actual input signals are a sudden shock. That is what I told you. Suddenly you might get, so you might have a sudden change in the input, so or you might get a constant velocity or a variation in the velocity also you can have, or you can have a constant acceleration, or it might vary. So it is very difficult to judge the actual input signals that your system will receive. For that purpose, the dynamic behavior of a system is therefore judged, and it is compared by application of the standard test signals like impulse signal, a step signal, or a constant velocity signal, or a constant acceleration signal. So by taking these signals, we are trying to analyze the system. So we are not taking the actual input signals. Standard signals are taken and the system is tested for those standard signals, and then it is given for the actual input. So another important of this standard signal is the standard signals are of great importance is sinusoidal signals. So along with these four standard signals, another important standard signal is sinusoidal signal. So let's take up these standard signals one by one. So the first standard signal is impulse signal. So this is the diagram of the impulse signal which is given to us. So this is the signal which can take any constant value only at the time t equal to 0, and it is equal to 0 for any other instant of time t. So here delta t is given by this equation. This is the symbolic representation of our impulse signal, which is standardly used for representation of impulse signals. It is taken as delta t. So delta t is taken as equal to a for t equal to 0. That is what it means. This is the amplitude. So it has a value only at t equal to 0, and it is considered to be 0 for t not equal to 0. And if the amplitude is taken as a, then the signal is known as unit impulse signal. So this is the basic signal which is used for analysis of any of the system impulse signal or unit impulse signal if the amplitude is 1 at the origin. Now coming to step signal. A step signal is usually represented as u of t. This is a standard signal which will have a constant amplitude towards your right time axis, that is, or the positive time axis. So it takes a value as equal to a for t greater than or equal to 0. That means towards the positive time axis it has a constant amplitude till it can go up to infinity also, and it is considered as 0 for t less than 0. That means here it is completely 0 towards your negative time axis. And if this amplitude a is taken as equal to 1, then it is called as unit step signal. That is a signal with a magnitude as unity. So this is the second standard signal which is generally used to analyze the system. And the next standard signal is a ramp signal. A ramp signal will take a shape like this. It's a linear signal. Okay. So with some particular amplitude, or it is also called as constant velocity signal. And this ramp signal is usually it is represented as r of t is equal to at for t greater than or equal to 0, and it is 0 for t less than 0. And if a is equal to 1, the ramp signal is usually called as unit ramp signal. That means whatever is your t value, that itself, for example, if t is equal to 0, your amplitude is also 0. You can observe here. If t equal to 1, it takes the amplitude as equal to 1. And it goes like this. So this is called as your unit ramp signal, which is another standard test signal which we have. So this is the slope, that is what I showed you. Okay, a to a, it goes like this if you have an amplitude as a. So this is a unit ramp signal which is taking that is what I told you. If t is 0, it will be 0 and so on. Now coming to the next standard signal which is called as a parabolic signal. It's also called as constant acceleration characteristic signal. So here this is represented as p of t. Okay, so which is equal to a t square by 2 for t greater than or equal to 0, and it is 0 for t less than 0. And if this a is equal to 1, the parabolic signal is usually called as unit parabolic signal. So it has a parabolic shape like this. So this is the fourth standard signal that we are going to use for the analysis of the system. So this is a parabolic signal with slope as equal to a. So wherein you have a gain as equal to 0.5a, 2a, 4.5a and so on. You have your unit parabolic signal which is taking the values 0.5, 2 and 4.5 and so on. So coming to the relationship between the standard signals, your impulse signal is represented like this, your step signal is represented by this equation as discussed previously, and your ramp is represented like this, and your parabolic signal is represented by this equation. So a step signal is nothing but taken as what? Integral of delta t, or delta t is nothing but taken as derivative of your step signal, and a ramp signal is taken as t into u of t. So by using one signal you can analyze the other signal. So ramp could also be represented as t into u of t, and step is taken as integral of delta t, and delta is taken as derivative, that is d u of t by dt, and parabolic signal is taken as derivative of your ramp. So there is a relationship between each of your signals. See, derivative of t is what? It is d. 1 minute. It is integral, sorry, integral of t and it goes like this, integral. Okay, so integral of one will give you the other signal, and if you reverse like this, derivative, that is what I told you. Reverse is derivation, forward is integration. Now coming to Laplace transform of these standard signals, Laplace transform of your impulse signal delta s is taken as a, which is given like this because it is just a constant a. So derivative of a Laplace transform of a constant is always constant. Laplace transform of your unit step signal is taken as a by s. Laplace transform of ramp signal is taken as a by s square. So derivative of your Laplace transform of t is always 1 by s square, and Laplace transform of t square by 2 is nothing but equal to 2a by s cube. These are the Laplace transform of the 4 standard signals that we are going to use for analyzing the feedback system. Now coming to time response of control system, time response of a dynamic system, it is nothing but a response to an input which is expressed as a function of time. So this is shown with the figure here. I have a system which I have taken here with some input. Okay, so we have two types of response. One is called as transient response, another one is called as steady state response. So we have two components in this. When we take the time response for a system, here as you can see I have one step signal and an impulse signal. For a step signal, this is the type of the response what I have got, and for an impulse signal, this is the type of the response which we have got. Now we'll see about these steady state response and transient response in the upcoming slides. Now coming to time response of control system, when the response of the system is changed from rest or equilibrium, it takes some time to settle down, obviously. So suddenly you will not get any response, so you need some time, you have to give some time for your system to settle down. Okay, transient response is the response of the system from rest to equilibrium to steady state. So please observe this. Transient response is the response of a system from rest or from equilibrium to steady state. And the response of the system after the transient response is called as your steady state response. This is the major difference. So from the rest or from equilibrium to steady state, whatever response I am going to get, that is nothing but your transient response. And after the transient response, whatever output response you are going to get, that is taken as your steady state response. That is, after reaching your steady state, the type of the response what I am going to get, that is called as your steady state response. So that is what is shown here. So here, from here to this state, this part is called as your transient response. And after reaching this steady state, whatever response I am going to get, that is nothing but my steady state response. So this is the difference between the two types of the response of the system. Now transient response, it basically depends upon the system poles only and not on the type of the input. So it basically is depending on the poles of the system. So it is therefore sufficient to analyze the transient response using only the step input. Whereas the steady state response, it depends upon the system dynamics and the input quality. So therefore, it is therefore examined using different test signals by final value theorem. So transient response, it is just analyzed using the step input, whereas steady state response is analyzed using the system dynamics and the input quality. So for that purpose, we are going to use the final value theorem to find out the steady state response. Now let's take an example of a first order system and we'll try to analyze the response for this system. So this is the transfer function that we have for a first order system with only one pole. So C of S by R of S is taken as K divided by Ts plus 1, where K is the DC gain and T is the time constant of the system. So here the time constant is a measure of how quickly the first order system responds to an unit step input. So this is a constant here we have, which is a measure of the quick response of the first order system for the given step input. And DC gain of the system is the ratio between the input signal and the steady state value of the output. So let's take an example of a first order system where K is taken as equal to 10 and time constant is taken as equal to 3 seconds. So here the DC gain is K equal to 10 and the time constant is equal to 3 seconds. Okay. For this particular system, we are going to get G of S as equal to, for another example, it is 3 divided by S plus 5. Okay. So for this particular example, you have to take 5 as common because you have to, here you don't have a coefficient for T. So take 5 common because the standard form is always Ts plus 1. Okay, K equal to Ts plus 1 is the standard form of the transfer function for a first order system. So but here this is not in the standard form because I have 5 here. So what you need to do is you have to take this 5 common and then that is taken as your standard form. That is why here I've got 3 by 5 and 1 by 5 by taking 5 common from the denominator. So for this system, the DC gain is 3 by 5 and the time constant is 1 by 5. So always whenever a transfer function is given for your system, try to express it in the standard form by taking the corresponding value as common. Now we will try to find out the impulse response for a first order system. Now let's take the first order system and the input what I am taking here is my impulse input because it is the impulse response what I am finding it out. So delta T I am taking with magnitude as 1. So unit impulse is taken as an input and this is the transfer function of the system what I have, K divided by Ts plus 1. Now R of S is taken as delta S, which is nothing but equal to 1. So C of S by R of S is nothing but equal to K divided by Ts plus 1 itself. Same response you are going to get. Okay, so C of S is taken as equal to what? K divided by Ts plus 1. So if I rearrange my term by taking T as common, C of S is taken as K by T S plus 1 by T. So I have a pole at S is equal to minus 1 by T. So the order represents the response of a system in time domain. We need to compute the inverse Laplace transform of this above equation. So if for this equation we are supposed to find out the inverse Laplace transform to find out the type of the output that we are going to get in the time domain. So when you take the inverse Laplace transform for this, the standard inverse Laplace transform what I have is C divided by S plus A is nothing but equal to C into e power minus AT. So if I apply this, I am going to get C of T as equal to K by T e power minus t by t, because here in place of a I have 1 by t. Okay, so here the constant value is k by t, which is getting multiplied. So this is nothing but my c. So k by t e power minus t by t. So it's an exponential response what I am going to get for my system for an unit impulse input. Now if we take some value for k and t, if k equal to 3 and t equal to 2 seconds, this is the type of the response I am going to get, which is an exponentially decaying signal. So it is what, 3 by 2, so 1.5. We will be starting from 1.5 and it goes like this when we replace the value for t as equal to 2, 4, 6 and 8. So it's an exponentially decaying signal response what I have got for the impulse input that is given for the first order system. So you can take a few values and you can analyze the type of the response what you are going to get for this particular system. So in today's session we have discussed about standard test signals. So the four important standard signals which is used for the time domain analysis of the system is impulse signal, step signal, velocity signal, acceleration signal, which is also called as ramp signal, and parabolic signal. And we have learned how to find the Laplace transform for all these standard test signals. And here we have taken an example of a first order system with the transfer function as k divided by ts plus 1, and then we have tried to find out the impulse response for a first order system in today's session. So I hope today's concepts you have followed, and these are your references for the topic. So you can refer any one of the book which is listed here for the concepts what is taught in today's session. Thank you all. Have a nice day. Jai Shri Gurudev.